Here we are, week 8. We've got a midterm this week. So we're doing a lot of concept review. We've got a lot of concept questions in office hours today. We're going to start with thinking about thermo and equilibrium. That was one of the questions. Then we'll talk about how pressure plays a role in equilibrium, which is kind of like a special case inside of this. And then we'll shift over to voltaic cells and talk about that. I don't have specific questions to work on, so I'm just going to talk through things, and you just have to slow me down and ask me questions as I'm going. Otherwise, I'm not going to know if I'm covering the things you want. Okay, so we started the quarter talking about calorimetry, talking about this idea of delta H, this enthalpy of a reaction. And we said if we want to figure out whether a reaction was going to happen or not in a spontaneous or non-spontaneous way, we can relate to this Gibbs free energy. But this didn't work out. It wasn't like the two were exactly equal to each other. There was some cost. Sorry, I'm going to tuck this away real quick. I don't like having my cell phone on me during office hours. It's distracting. So we had this direct kind of relationship, and we said it didn't work out this way, though, right? Delta G, our energy available to use, was not directly equal to our enthalpy released from the reaction. So we said there must be some cost in terms of like where our delta G actually ends up, and that was this minus T delta S. So we noticed it depended on the surrounding temperature. What environment were we in? Were we doing this in a freezer? Were we doing it inside an oven? Were we at high temperature, low temperature? That had an effect on whether the reaction happened or not. So this T delta S term takes that into account. And then we had this delta S term, which was a really weird one for us, right? Entropy. And there's a lot of different videos you can watch on trying to get your head around the idea of entropy. But entropy is essentially, there's a cost to having energy densely together. Energy tends to distribute, energy tends to spread out. And so this delta S is kind of this way of like, you know, the example I used in class was you take a hot piece of metal, you put it into a cup of water. What happens to the water? Water warms up. We all know that happens conceptually. We've all had that experience. But when we start to think fundamentally, why does the water warm up? Why does the metal give away its energy? That's going to be this idea of entropy. It's this this fundamental idea of like energy dissipation. So if we've got some amount of energy, we want to use it, we also have to take into account that there's energy dissipating as well. So there's a cost to keeping energy condensed together. We say, cool, we can do this kind of experimentally. We can think about this in different chemical systems. We could think about it in terms of a solid dissolving in water. What can we say about that? Delta H, what can we say about delta G? What can we say about delta S? We kind of came up with this idea of delta G, and we said it could be greater than 0, it could be less than 0, greater than 0, or equal to 0. And this would tell us whether it was going to be product favored, reactant favored, or equilibrium. So this one was reactant favored. Product favored, and equilibrium. And there was another way we talked about it before we started talking about it in terms of reactions. We said non-spontaneous right? And we moved away from that language, even though that's the language that was used in our development of the idea. It was used in terms of kind of physical processes. We said if we want to do this for chemical systems, when I write down a chemical reaction, it's either going to go towards products as written, or it's going to go towards reactants as written. So it's going to go one way or the other as it's written down, or nothing. And so this idea of spontaneous, non-spontaneous, we have to toss in this extra language when we're thinking about it in terms of chemical reactions. It's spontaneous as written means that it's going to go towards products as it's written down. Non-spontaneous as written would mean that it's going to stay as reactants as written down. And so just saying reactant favored, product favored gets us away from that kind of extra complexity in the language. So now we can look at a chemical reaction and say, based on the delta G, is it likely to go more towards reactants or more towards products? And this is, you know, for the equilibrium. And so we could start thinking about that. We introduce this other equation, delta G equals negative RT ln KEQ. This allowed us to start to think not just about the chemical reaction and whether it's going, where it ends up, but kind of, this tracking value for how much is it going to end up products or reactants. And we introduced this idea of KEQ. It's going to be the concentration of products at equilibrium versus the concentration of reactants at equilibrium. Recognizing that the exact expression for KEQ depends on the exact reaction we're looking at. This is going to be like product times product times product divided by reactant times reactant times reactant. You get your, like silver squared times chloride, whatever you're doing. So at equilibrium, rather than just saying it's reactant favored, we could get an exact ratio of how much products to how much reactants when we get to that balance point. How much products, how much reactants do we want to get to from our standard conditions? And that idea of how we get there allowed us to say, well, what if we did non-standard conditions? What if we looked at delta G without that superscript 0? What if we looked at non-standard conditions? And we ended up with RT. I'll do it. Do I want to do it? I'm going to do it a little bit of a weird way. This is not how we usually write it down, but people get mad at me when the negative sign disappears, so I'm just leaving it as the upside down. I think this is fine, right? Some logarithm rules in there, right? So we get RT ln KEQ to Q, where Q is our reaction quotient. It's products to reactants at kind of any value. And so what delta G tells us is not just where we end up. That's what the standard value tells us, is where we end up. But delta G tells us how we get there. So delta G gives us slightly different information, where we've got, again, delta G greater than 0, delta G less than 0, delta G equal to 0. And delta G gives us this kind of how are we going to change in order to get to equilibrium? So a delta G less than 0 would tell us we need to move towards products more, right? So as the reaction proceeds, if our delta G is less than 0, there's still energy to be used there to drive the reaction. So we got to keep going, we keep going, we keep going. So this tells us where we're going to end up. This tells us how we're going to get there from some random starting spot. And if delta G is greater than 0, then we're going to go towards right, we have to keep going towards reactants. Question?
Can't you tell which way you're going to go from comparing the Q to KEQ though?
Yeah, that's essentially what we're doing with this delta G, right? So delta G is going to be greater than 0, right? So we can just kind of take apart this thing and say if KEQ is less than Q, let me see if I've got this right. Now let's see if I messed up here. Oh, because like I said, this is not how we typically write it. If KEQ is less than Q, this is going to, okay, I did it right. This is going to be a number less than 1. The natural log of something like 0.1 is going to be a negative number. Delta G is going to end up positive, right? If KEQ is greater than Q, then we're going to have, this is going to be like 1,000, 10,000, 100,000. It's going to be a number greater than 1. Natural log of that's going to be a positive value times the negative. Delta G is going to be negative overall. So yeah, after we recognize this, we say, oh, look, we actually don't need this whole delta G thing. We can just say, compare KEQ to Q. And if we're at that funny particular spot where Q happens to be equal to KEQ, that is the definition of the equilibrium point, right? We've got the right ratio of products to reactants.
Should we like memorize like if KQ is less than Q, it goes towards reactants, or
You
is
should
it
be
kind
able
of?
to figure that out each time.
Oh yeah,
Right?
that's what I was
It's just a little logic puzzle. I usually think about it in these terms, but this whole thing is how we get to these terms. And then after we do all that, KEQ. The nice thing about this little chunk here is KEQ will tell us whether it's product favored or reactant favored, just if it's greater than 1 or less than 1. And then KEQ compared to Q tells us if we're towards reactants or towards products. And so this box right here is actually the entire board, in my opinion, is like the entire board condensed down. Technically, we should have 3 more things. We should have KEQ greater than 1, KEQ less than 1, KEQ equal to 1. And I'm going to flip those. Less than 1 is reactant favored, greater than 1 is product favored, equal to 1 is coincidentally already at equilibrium. Like it's just perfectly balanced between the two. And the reason we use the number 1 is because that would be standard concentrations, would be 1 molarities for things. So that would be Q is equal to 1, Q is equal to 1, Q is equal to 1. So we can tell from standard conditions, are we going to go towards one direction or the other to get to equilibrium? And so that's kind of the big idea of the thermodynamics in equilibrium, right? Since the first exam, I don't know when you had, since the first exam, we really have been kind of stepping away from delta H and delta S a little bit more. They're still important. Delta G is kind of the important part. Delta H and delta S still come up in interesting ways because we can find those points where the temperature can make something change, whether it's product favored or reactant favored, whether it's towards products, towards reactants. We can essentially turn reactions on and off. That's pretty neat. But since the exam, we've really been focused on 2 different things. We've been focused on equilibrium calculations, like once we have this set up, what do we actually do with it? And then we've been kind of dipping our toes into voltaic cells.
I guess, okay, so I know like when we're doing equilibrium, you use like, it's when like you're using like delta G standard, right? Or like standard conditions, or can equilibrium?
Not always.
Okay.
Should we do an example and kind of get an idea?
Yeah.
Let's do an example. Okay. Okay if I erase all this? I'm going to leave this stuff in the box here. I think that's going to be useful soon. Okay. So we've got our standard, we've got our non-standard, we've got to get away from the idea of spontaneous and non-spontaneous. This is a pretty broad review, pretty quick. That was like 3 weeks worth of class in like 15 minutes. But we've spent a lot of time on it, so hopefully that's just nice refreshers and you're like, yes, I've heard all of these things. So we say, okay, how do we actually use this information to do something interesting? We'll go, let's do, I think I'm going to have to pull up an example real quick because most of the examples, I was trying to come up with an example off the top of my head, but all of the examples I was coming up with off the top of my head were things that are like billions of times more products than reactants. So I was thinking of combustion reactions. And combustion reactions are always kind of boring because they're like 99.999999999999999% products. So we can just do stoichiometry with them, not really worry about all of this equilibrium stuff. But there's one, is it in this lecture or the previous lecture? There's one, and I particularly want to do one with gases so we can do this pressure idea as well. Carbon monoxide. Let's try this one. This is an example that I have in my slides as like another example we could do. I don't know how relevant this reaction is, but let's do this. We're looking at a chemical reaction. We're looking at methane gas reacting with water gas. And this can go through some sort of chemical reaction to produce CO2 gas and H2 gas. You might be looking at this and be like thinking, wait a minute. Do these things, because methane gas is like when you turn on your gas stove at home, that's like methane gas. And you might look at this and be like, wait a minute, if I like boil water over my stove, am I making hydrogen gas? Bum, bum, bum. Not really, right? The equilibrium constant, I didn't give myself enough space to write the equilibrium constant, so I'll just put it out like over, I'll just write it here. We'll put it down at the bottom for a moment. The equilibrium constant for this chemical reaction is 3.91. So this is not a to completion type reaction, right? This is not, my K value is not equal to like 3 billion or 5 billion. This is going to be like maybe some products are made, but not like a ton like we've seen with our previous stoichiometry. And that's where this equilibrium stuff really starts to get weird, is because everything we looked up to, every chemical reaction we've looked at up till now have been reactions that always go to completion, so we just do stoichiometry and it's good enough. It's only after we understand enthalpy and entropy that we can start to look at reactions that don't go to completion. And it turns out most of the interesting chemical reactions, well, not most, but a significant number of the interesting chemical reactions in the world are ones that don't go to completion. They're not these like easy stoichiometry problems. They're these equilibrium problems. So the problem I have set up says, let's say we've got some initial conditions where we've got 0.2 molarity CH4, we've got 0.4 molarity H2O, we've got 0 molarities here. Right, and when we look at this, we say, okay, I want to know, before I go, I'm going to think about how this is going to change. And I need to know, is it going to change towards products or towards reactants? To figure that out, I look at my initial, and I can essentially say the initial is where I calculate my reaction quotient to figure out, compared to the Kc, is it going to be towards products or towards reactants? If I have 0 products, can it go towards reactants? Is there anything over here that can react and push this way? No. Right? The Q, if I calculate this, I'm going to have 0 times 0 divided by 0.2 times 0.4. Mike, come on in, grab a seat someplace. I'm going to have, essentially, my Q value is equal to 0. In these situations where I have no products, my K value, my equilibrium constant, is always greater than 0. So if I've got 0 products, my equilibrium is always going to be towards products because it's got to be non-zero values. It might be a teeny tiny amount towards products, but it still has to be towards products. So when I look at how is my system, my setup of my system going to change, once I have this set up, I like freeze it in my mind for a second as soon as they mix, and I say, now what? It's got to change. And it's got to change such that I lose some of this, I lose some of this, I gain some of this, and I gain some of this. And before I take any other steps, I'm going to double check that this is balanced, because the change step is going to get messed up if it's not balanced. I think it is. Oh, it's totally not. It's totally not. So these are going to be wrong. We've got to fix those. If we don't balance our chemical reactions, we get our change step wrong. Doesn't matter for the initial, because that's just where we're starting. That's the concentrations we have. But this changing is going to depend on the stoichiometric ratios. So I got to balance this big time. Okay. We got 2 oxygens. We'll do 2 there. That's got 1 carbon, 2 oxygens, 2 oxygens. 4 and 4 is 8 hydrogens divided by 2. 4 there. And I know that's right because I actually had it balanced on the slide and I just didn't pay attention to my sample problem. So I look at this and say, oh, drat. I've got to change this. For every 1 mole of methane used, 2 moles of water is used. So I have to have that stoichiometric power, that stoichiometric value in there. For every 1 mole of CO2 made, 4 moles of H2O are made. there's going to be a 4x there. And that's the stoichiometric way in which this thing is going to change to get to equilibrium. And after it goes through that change, I'm going to have 0.2 minus x. I'm going to have 0.4 minus 2x, and I'm really worried about what I've done to myself here. Oh, I don't know if x, I don't think, with that k value, I don't think x is going to be small.
That's true.
So, find the chemical equilibrium condition.
Oh, it gives you x. Or you gave x.
Oh, I must have solved that. Okay. I set up a problem that was way harder. Let me check something real quick. This is why I get in trouble when I just like grab problems. So I had it set up. I eventually gave it. Okay, I know what I did here. Cool. So we're going to have 0 plus x. I'm just going to write that as x. And I'm going to have 0 plus 4x. I'm just going to write that as 4x. And now we say, okay, if those are my equilibrium values, right, here's my equilibrium family. I could write down Kc is going to be products over reactants. That's going to be my H2 to the power of 4 times my CO2 concentration divided by my CH4 concentration divided by my H2O concentration squared. Then I can plug in my Kc value and my equilibrium values and get what equation I actually need to solve. 3.91 is equal to 4x to the 4th times x divided by 0.2 minus x. I'm like getting nervous as I write this down. 2x squared. I'm like, oh my goodness. And we look at this and we say, okay, this is not a quadratic to solve. This is not a third root equation to solve. This is going to be a fifth root equation to solve. So we're going to have to set up a fifth root equation system and solve it. And we say, we don't want to do that. Let's use the x is small approximation. And then we say, well, hold on. Can we use the x is small approximation? How does my equilibrium constant compare to my initial values? My equilibrium constant is bigger than my initial values. I think x is small is going to fail. I don't think we can use x is small. Just for fun, let's see what happens if we did use x is small. I'm going to do it in orange. Well, let's do it in red. I'll grab my red pen. We'll do this in... That's okay. I just wanted to make sure it's still recording. So we're going to do it in red here. I'll need that number in a moment. We're going to do it in red here because I think this is going to be terribly wrong. So if we did x is small here, which I don't think we should, let's just see what happens when it goes bad. We're going to have 3.91 is approximately equal to 4x to the 4th times x divided by 0.2 times 0.4 squared. That looks really solvable, but it looks like it's going to be, well, let's see what we get. One of the things that's kind of funny is I have to do 4 to the power of 4. I should probably know that's 256 off the top of my head, but I didn't. So I'm going to do inverse times 3.91 times 0.2 times 0.4 squared. I'm going to get 4.8 times 10 to the minus 4 is equal to x to the 5th. I'm going to get x is equal to I'm going to get x is equal to 0.21. What, is that a good... How's that look? If I do 0.2 minus 0.21, what happens? We get negative constant. That's terrible, right? We can never, whenever we're at equilibrium, at the end of a chemical reaction, we cannot have negative molarity or negative moles left over. During the change step, sure, that's how it's switching. But at equilibrium, we can't have negative moles stably in a container. So X is small is a big fail. In this case, X is small fails. We kind of thought that was going to happen because we looked at that equilibrium constant compared to our initial concentrations, and it looked like bad news. Question?
On like exams or quizzes, like would you give us problems where you expect us to like sub out the X when we say the X is small? Or like would there be problems where
Any problem I do, I would always tell you to use the X is small approximation, even if it's terrible, but then I would want you to do this type of analysis afterwards. Like, was the X is small approximation a good idea or a bad idea? And, you know, like that thinking is more important to me than seeing if you can solve a fifth root equation, right? Because we're not a math class, we're a chemistry class, so I want to see your chemistry thinking.
Wait, where'd you get 4.8 times 10 to the negative 4?
That was 3.91 times 0.2 times 0.4 squared divided by 256,
Okay.
which is 4 to the 4th. So I did all of my math rearranging on the calculator. I could do all that pretty easily. Question?
So let's say you had a concentration on the right side.
Mm-hmm.
How would you?
Only one concentration?
Or both of them had a concentration.
Ooh. That would be interesting.
How
Right?
would you like analyze? Because at the start we decided that it's gonna go towards.
Let's
reactant.
finish this problem and then we'll change it up and see what happens in that case if we had 4 things there.
Okay.
We didn't have to do much for this one because we could pretty easily see that Q was going to be 0, and so we knew that K was going to be bigger than Q. If we have things on both sides, we have to do that K versus Q comparison to figure out where the minuses and pluses go.
Yeah.
Right? Because we might end up with minuses on the product side and pluses on the reactant side if we're going towards reactants. But we'll look at that in just a moment. We'll finish this one first. So, to finish this one, we can't do X is small. That didn't work. Didn't work. Can't do it. So, I went ahead and I plugged it in. Yes, problem from lecture slides that I just randomly picked up. So we have to set up, we have to open up like an online solver, or if your calculator can do fifth root equations, we have to set up this equation and say solve for X. What's that?
Calculator can't do it.
Your calculator can't do it?
No, it says there's no sign change, so it can't estimate the value.
Oh,
I don't know what that means, but
weird. I was able to do it with an online solver.
I think TI might not be strong enough for this one.
Or maybe there's like, maybe I've got the wrong thing on my lecture slide, or maybe it was just like a mess up in the setup.
Sure.
Can I see? Yeah, see?
Yeah, so you do this, and then you just press this one after.
4x to the 4th times x point 2x to the 4x squared. Yeah, that looks.
And you press OK, and then you press it again. And then if you press it again, then it gives you, because it solves it after you have to press solve. And then it gives you the answer. But then it like says that there's no answer. Like they can't find an answer.
Connect to the internet or like. But I think.
Huh.
Because the X that's there is from a previous problem that I did.
Oh, gotcha,
It's not regarding this X.
Okay, weird. Well, I'm gonna go with the number that I have on my slides. This is a fifth root equation, so you should get 5 different answers for X. And then it turns out only one of them is realistic. I would never do this to you on quizzes or exams. Like I said, on quizzes and exams, we'd always do the X is small and then analyze it. We wouldn't actually like solve a fifth root equation. Some of the answers are going to be imaginary. Imaginary answers, don't use those. Some of the answers are going to be negatives. Those probably aren't going to be right. One of the answers should work though. Question?
For like the X is small evaluation, would the like end thing be like, oh, it's negative, so it doesn't work, or would there be like other possibilities where?
Yeah. So the other possibilities, right? The thing that we're looking for when we're doing our analysis is we are looking for X divided by concentration of our initial things is greater than, is less than 0.05. So that would be less than a 5% difference. It's not technically percent error, but it gives us a quick way to check.
The concentrations being like 0.2 and like 0.4.
Yeah, since we're using the x is small approximation twice, we have to check both of those. Now, if we do 0.2 over 0.2, that's like 100% error. That's not going to work. If we do 0.2 divided by 0.4, that's only 50% error. Still not going to work for us. So we would do a comparison like that and be like, this x value is way too large. We cannot approximate that x is small.
Can you get like 4 imaginary and 1 real answer?
Is the real answer 0.01343?
Well, for me, like I think I got mine to a 0.12.
0.12? Okay. Well, we'll see. Oh, this is hard to read. So yeah, you end up with 5 different answers. Most of them are imaginary. One of them ends up being real. So this is the answer I got. We're going to go with it. I made these slides a long time ago, so I don't know if this is perfectly correct. But we're going to go with it, right? So at that point, after we solve for our x value, then we can plug x in for the different values up there, and we can find our equilibrium concentrations. So in that situation, we'd have, and this, I tried to solve it for an exact value. Again, I hope I did it correctly. If you're watching this at home, you can use your favorite online solver and see what you get. So in this situation, for this 0.2 minus x, I would get 0.0657. 1343 times 2, negative, plus 0.4. This value for my H2O left over, I'm going to get 0.1343. My x, oh, we can even check if this is right. This is going to be 0.1343, and this is going to be 0.1343 times 4. 0.5372. And I'm going to do a quick check. If I plug these values back into here, do I get 3.91? Let me think about this. That times that. No, I get something a little bit off. I'm trying to go too quick though. If I plug these numbers back in, so I think this answer is wrong too. In any case, if that x were correct, I'll have to double check what's going on here, but these are the values we would get for our equilibrium concentrations. I can tell something's wrong here, again, still, because when I take these different values and I plug them in here, I don't get 0.391 back. I'm not getting 0.391 back. Unless I'm just doing... Oh, okay, no, it's because I did math wrong. Let me check something real quick. 1657. Why is that? I'm getting, I think, okay. I'm seeing a typo in my previous work. Okay. I see a typo on my lecture slide, so we've got a problem here. I'll have to fix it later. I wonder if I did some reverse solving and just did it incorrectly. In any case, that's how you'd go through an equilibrium problem, more or less. I would not give you something where you actually have to solve this fifth through. We'd always do it with the x is small and then say whether that was valid or not. I'm going to pause this real quick. This is bothering me. So back to recording. We corrected this. It should be x is equal to 0.1229. I don't know what I did before. I found a typo on my PowerPoint slide where I think I did this subtraction wrong. And so I think I set something up incorrectly there. And the reason I knew something was wrong was because I was doing this check where I take these numbers, I plug them back in, and if these are actually the equilibrium values, this whole thing should be equal to 0.391, which it now is. So those are the corrected values. If it looked like it was just a blink of an eye, that was because I was paused so I could fix this. It was bothering me. This is the correct value. Again, I used an online solver. I used the Wolfram website. They have a really nice online equation solver. I'm not sponsored by them, but I'm also a fan of their software. I used their software during like my graduate school work and all that stuff. They make some really cool software. So we have a couple other follow-up things that we can think about. Questions about this?
Are you allowed to use Wolfram doing tests?
No. But like I said, I would never actually ask you to solve a fifth root equation during a test.
Okay.
Come on in. If you're comfortable sitting on the floor, let's just keep backpacks tucked under desks and chairs and stuff. So this was kind of when we had some starting reactants and no products. We said, what if we had products? Okay, so I'm going to erase all of this and we're going to get to a new problem. Ready? Okay. So then we say, okay, what if... Oh, I didn't mean to erase the KC. Whoops. KC is equal to 3.91 still. What if instead of starting with 0 CO2 and 0 H2O, what if we started with something? What's your favorite number? Did you get your question answered, or are you just like...
Oh, I just have to go.
Okay, see. Okay, let's say this is 0.44 molarity here. What's your favorite number?
17.
Okay, let's say this is 0.17 molarity here. What if we've got all things present? Now what happens? This is where we have to go back to KEQ versus Q, right? Without really doing any calculation, we could tell how it was going to change because we knew we needed more products. In this situation, I can't tell. So I have to calculate, instead of just eyeballing my Q value, I actually have to calculate my Q value in terms of products over reactants. I have to do 0.44 times 0.17 to the fourth divided by 0.2 times 0.4 squared and get a value associated with that initial condition. Right? I don't know how these four things all got pumped into the container without reacting, but it's kind of a thought experiment. So all four of these things got pumped in. We got 4 entry ports, pump, 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 pump.
Wait, why do we need to find the Q?
Because we don't know which way the reaction's going to go. Is it going to
we
go?
don't know which one is...
So with all of these things here, does it need to go towards products or towards reactants to get to equilibrium?
Oh, to figure out what to subtract from. And
Yeah.
What to add. Okay.
So we don't know if it's going to go towards products or towards reactants. So I do 0.17 to the fourth times 0.44 divided by 0.2 times 0.4 squared. Sorry, oh, I typed it wrong. Someone help me out. 0.17 to the power of 4 times 0.44 divided by 2 divided by 0.4 squared. Okay, I think I got it that time. I think I got the same thing twice. I thought I hit something wrong with my calculator. My Q value with these initial conditions is 0.00115. And I can look at that and I can say, look, my KC is bigger than my Q. I still need more products than I have to get to equilibrium.
Could you not have also just said that the KC value is greater than 1?
Well, the KC value is greater than 1, so that tells me that I tend towards more products. But if we think about this in terms of our Gibbs plots, right, here's my 1. You know, it's just a little bit greater than 1. What if the initial conditions we set up were already over here? What if they were already, right, so if that H2 gas was like 0.67 instead of 0.17, then it would go the other direction. Right, so it's a matter of, right, where am I relative to, here's my KEQ value. My initial conditions can be anywhere along this curve. They could be places over here, where I don't have enough products yet, and so I need to make more products. They could also be over here where I don't have enough reactants, so I need to make more reactants. A couple ways we could do that, right? If that H2O gas dropped in concentration, maybe we'd get over to this regime, right? That's a check we should do. And I can't eyeball it from my Q. I know that the equilibrium value is going to be more products than reactants. And I guess just by looking at this, you could kind of say it looks like there's still not enough products. But with the power of 4 and the squares in there, I can't eyeball it. I need to do the math. And after I eyeball it, I'm going to have a problem that I would never ask you to do, right? I'm going to have a minus x, minus 2x, plus 4x, where there's no zeros now. It's going to be a fifth root equation again.
So,
And I wouldn't do that to you. I wouldn't make you solve something like that.
when you have all of them like this, and then you find the Q. So since we found that the reaction is going to go towards products, that means that we need to take away from the reactants and add to the products.
Exactly.
Okay. So going towards. So what we're doing is we're modeling how it would go towards products.
Yeah.
Okay.
Right. So the whole point of the change step is to figure out how this reaction changes, how it behaves to get to the equilibrium. That's right.
So if your KQ is greater than your K, you would know that you're going in a reverse reaction, so your change would be in the reactants.
Yeah.
the
So the
subtraction.
minuses and the
Right.
pluses would flip where they are. Yeah.
Okay.
So the other thing that people were asking about was, what about pressure? And I particularly wanted, who asked about pressure? Did they leave? It doesn't matter if they left. Right, the pressure question was, how does pressure affect equilibrium? For any of our aqueous solution cases, doesn't really do much. For our solid cases, doesn't really do much. For our gas cases, it gets interesting. And this is a Le Chatelier's principle type idea. Right, and so Le Chatelier's principle says, you know, if I increase the amount of reactants, then it's got to tend towards products. If I increase the amount of products, then it's going to tend back towards reactants. If you disturb a system that is at equilibrium, it will push back towards equilibrium. So we get to some equilibrium value, and then we start cranking up pressures and stuff like that. And there's a couple different ways that we could change the pressure. If we change the pressure of any individual component, right? One ideal gas law, we all okay with that?
Mhm.
Yeah? So, forgetting this for a moment, if we're thinking about just how the pressure change goes, we've got PV equals nRT. We can essentially set up a kind of like concentration thing where pressure over RT is equal to moles over volume. So we can look at our moles, let's just do it for CH4. I can look at my moles of CH4 relative to the pressure of CH4.
And this is to.
This is for the pressure. We don't actually have to do it this way. The point is that moles and pressure kind of relate to each other. So if I increase my moles of CH4, that's the same as saying increasing the pressure of CH4. So if I increase pressures, I mean, it's essentially the same as saying increase that number of moles. So if I increase my amount of CH4, that's increasing reactants. The reaction is going to go towards products more. If I increase my pressure of H2 gas, that's like increasing the moles of H2 gas, that's going to go back towards reactants.
How is it like increasing the moles? Like, how is increasing the pressure like increasing?
So how do you increase the pressure of that one component? You got to pump that one component in.
Oh, so you're basically, increasing the pressure is adding more.
Yeah,
Oh, okay.
that's what
That
I'm
makes
saying. It's
sense.
essentially, right?
Okay.
So the only way you can increase the pressure of just H2 is by just putting in more H2.
Okay.
Now the place that becomes interesting is, what if we increase the pressure of the entire thing? So I'm increasing the pressure of the CH4, the H2O, the CO2, and the H2 all at the same time. I'm just increasing the pressure of everything. Well, in that case, we have to take into account the fact that the pressure effect is going to have essentially a 4x effect on the hydrogen gas, a 2x effect on the water vapor, and only a 1x effect on the CH4 and CO2. Right? So increasing the pressure of all of these things at the same time the only way you could really do it is by decreasing the volume, right? And that volume decrease is not going to affect these two concentrations. Well, it's going to affect these two concentrations the same, but this concentration is to a power of 4, this concentration is to a power of 2. So that change in concentration gets amplified by that power of 4. So an increase in pressure usually pushes us back towards less gas molecules, is the simple way to think about it.
You can do an ice table with pressure too, right? Like it would
You
just
could.
Like, is that kind of what you're talking right now, or is this different from doing an ice
It's
table with
closely
pressure?
related, right? So the point is, you can do an ice table with pressure, but that's kind of like doing it with molarity. You're just off by a gas constant in temperature term.
Mm-hmm.
If we're doing at 25 degrees, I erased my R there. Right, so it's the textbook does a little bit more on this. We didn't do much of it.
Would something like this be on the exam? I guess, like, I understand how to do it with pressure with the ice table, but with this, like, with using this, I'm, like, more, like, unfamiliar with how to, like,
this is, we don't have to do any of these calculations. This is just conceptually. If we increase the pressure of the entire system, or, like, if we did it with solutions, we didn't do it with pressure. If we did it with solutions and we somehow removed the water from the solution, right? By removing the water from the solution without removing anything else, you've increased the concentration of everything.
Mm-hmm.
If everything was a 1-to-1 mole ratio, it wouldn't matter, everything would cancel out. But here we can see concentration to the fourth over concentration squared, that concentration effect is going to have a bigger impact on the top there. So as that volume goes out, that concentration on top, that concentration of products is going to get bigger. It's going to get bigger on the reactant side as well, but the fact that it's concentration to the fourth instead of concentration squared is going to have a bigger impact on products. Same thing with pressure.
So, like, it would increase the Q value.
You'd essentially increase the Q value if you were increasing the concentration.
Mm-hmm.
And if you're increasing Q value, then you could get to a point where you don't go towards products anymore.
Mm-hmm.
And so you're changing your Q value essentially by doing that.
Also, sorry, I know you just said it, but I forgot to write it down when you answered it. But so this reaction, because it goes towards products, we're gonna do subtraction for the reactants and addition for the products. Okay,
so from what we figured out here with this comparison, it's going to be minus x minus 2x plus x plus 4x. Our x values in this case compared to what we already did should be smaller because we've already got some products made. And if I was smart, I would have had my answer written down from last time and I'd be able to tell, like, because the equilibrium values should still essentially, oh no, the equilibrium values are not going to be the same values because we've got other material already there. Right? I didn't do something to balance total moles. I had random made up numbers. So my equilibrium value, my x value is going to be different. Right, so this pressure idea is really just kind of, the way I think about it is I've got, when I'm looking at this, I've got 3 moles of gas on my reactant side, 1, 2, 3, and I got 5 moles of gas on my product side, 1, 2, 3, 4, 5. So any change in pressure is going to have a bigger effect over here because there's 5 moles of gas getting affected versus 3 moles of gas getting affected. So if I increase the pressure, I'm going to push back, like if it's at equilibrium and I increase the pressure, that's going to be like making this Q value bigger. And if I was already at equilibrium, I'm now going to make the Q value bigger than the equilibrium value. If Q value is bigger than the equilibrium value, I have to go back towards reactants. If I decrease the pressure, that would be, if I was at equilibrium, that'd be like taking this Q value and making it smaller. And if I was at this point where KEQ is equal to Q, and I make the Q value smaller, then I'm in this situation, I have to go towards products. So it's really, if you're at a point where Q is equal to KEQ, and you're doing some shift with pressure or concentrations or whatever you're doing, are you pushing it towards this situation where your Q is getting bigger, Or are you pushing it towards the situation where your Q is getting smaller? Right? How are you disturbing your equilibrium? Because nature is going to, like, when I say nature, I mean the enthalpy, entropy, those thermodynamic drivers, those energetic drivers are going to fight against you, essentially, and say, nope, back towards equilibrium. This is the struggle of life. Everything we do pushes things out of equilibrium a little bit, and nature's like, nope, back to equilibrium. Every building we build is fighting enthalpy and entropy. And if we don't do anything to maintain it, it crumbles down, back to equilibrium. It takes a lot of energy to build those things. Good longevity, but eventually, back to equilibrium. That was really to get at this pressure and equilibrium idea. Was that how, I don't know if that was anyone who's still here, if they left. We had a lot of like deep concept questions, so we just kind of been doing like an hour-long review of the last 2 weeks of class. Did that one. Those of you who came in about 10 minutes ago, did you have any specific questions I should throw on the list we're about to switch to talking about voltaic cells.
I was just confused about the procedure from the equilibrium lab.
We'll talk about that some. Oh, from the equilibrium lab. Okay. And specific questions for you?
It's the same issue my lab partner and I were having last time we talked to you.
Still?
Well, so she emailed you and we found a mistake on her end, but I had it right.
Magic board eraser, because it was paused while I was erasing. Okay, so we are now moving on to talk about voltaic cells. And the switch to voltaic cells was kind of chunky because when we were looking at acid-base reactions, we were using Ka. When we were looking at precipitation reactions, we were looking at Ksp. But when we look at redox reactions, we use E cell standard, where E cell standard is equal to negative NF. Wait, no, I've got this backwards. Hang on. Where E cell standard can be related to KEQ. And it's through the equation negative RT ln KEQ is equal to negative NF E cell. So we're still using something that is like an equilibrium constant. Standard cell potential relates to the equilibrium constant. But the things we're doing with the voltaic cells are shockingly different from what we've done with our other chemical reactions. And we saw this in my favorite example when we were doing the concentration cell, but let's skip that one for now, right? Essentially what we're doing, let's do the silver-copper reaction, because we did that one in lab in 124, right? And we saw that if I had Ag plus aqueous, and I mixed it with copper solid, that would go through some chemical reaction and make Ag solid, and it would make copper 2 plus. And I know that it's making copper 2 plus because the solution turned blue and blah, blah, blah. Right, so that chemical reaction just happened. And where we saw this happen was we had a beaker, we had some liquid in there, we had a stick in there of copper, and then just from the copper sitting in there, we saw like little hairs start growing on the piece of copper. Do you remember that? Pretty fun reaction. You might not remember that, but people had 124 last quarter, right? And what we actually saw happening was silver precipitating out. And what's happening is right on this surface, and then copper ions going into solution. So there's electron transfers happening right on the surface where electrons are leaving into the solution, into the Ag+, and the Ag+ is taking that electron and becoming Ag solid. Right? And so right on the surface, there's this transfer of electrons happening. And it's like, cool, we can explain redox reactions through this electron transfer energy. The place where all of the language and all of the setup kind of gets weird, in my opinion, is because people were doing physics on these things at the same time people were doing chemistry on these things. And what physicists were doing and what chemists were doing seemed very different. And so they developed different language around what the physics people were doing and what the chemistry people were doing. After like 60 years of them doing work separately, they came together and were like, oh, it's the same thing. And so that's where a lot of this like double names for everything comes from, is the fact that there were like two different groups of people working on it. Chemists were doing it from like this type of setup where it was reduction oxidation reactions. How is oxygen affecting things? How do other things behave like oxygen with oxidizing agents? Whereas physicists were doing this weird thing where they were like, I got these metals and I can make electricity out of them. But they had to do a relatively special experimental setup in order to make electricity out of them. And so what they were doing was they were creating voltaic cells. They were getting a beaker with a stick of copper metal in it and a bunch of copper solution. And then they were getting a second beaker with a stick of silver in it and a bunch of Ag plus in solution. Right? And at its first look, it's like, that's not going to do anything. Copper in touch with copper plus ions, that's not going to do anything. Silver in touch with silver ions, that's not going to do anything. But because of the way that this has some electronegativity versus this, right? This is going to draw electrons towards it more than copper is going to hang on to its electrons. They've got that difference in electronegativity, that difference in electric potential, if you want to use that word. If I connect these with a wire, the silver will start pulling electrons, the silver ions in particular, will start pulling electrons towards it. And that will make this electrode start to grow bigger and bigger as silver metal starts to plate on the electrode. That will make this electrode, the copper electrode, get smaller and smaller as the copper falls apart into copper ions. Now, this setup would stop working really quickly because all of the plus ions will like rush towards the electrode and it'll create this like weird charge imbalance in the solution. All of the 2 pluses will run away from the electrode and will create this weird charge imbalance. The way we deal with that charge imbalance is we set up I'm going to give it an extra label here. We set up a non-reactive salt bridge. In this case, nitrates are usually pretty good to use because nitrates don't precipitate. The reason I said particularly, if you use sodium chloride in this salt bridge, you'd mess up your battery because silver ions would precipitate with the chloride and you'd mess up your solutions. Sodium's also a good thing to use. It doesn't really precipitate with anything. Its reduction potential is far enough out of the way that it doesn't really matter. Nitrates sometimes cause problems because nitrates can go through redox reactions, and so there's places where you like can't use nitrate. It'll react when I don't want it to. Generally is okay, right? But sometimes we have to watch out for that. So we just got to make sure our salt bridge is non-reactive. It's not going to go through any acid-base precipitation or redox reactions unexpectedly.
Wait, so the salt bridge is taking the electrons that are going over to Ag?
The salt bridge, right, as these Ag pluses go, the salt bridge will dump some non-reactive cation in there to take place of the silvers that are leaving. And it'll also dump some non-reactive, let's say NO3 minus, into the solution over here to account for the fact that a bunch of positive ions are showing up. And so it keeps the solution's charge balanced without dealing with the electrons. The electrons are running across the wire. So we have to deal with ion concentration and electrical charge. And so the salt bridge is just there to take care of the ion concentration. Right, okay. So we end up with this really weird experimental setup, right? The redox reaction, we saw that in 124. You throw a piece of copper metal into silver ions, redox reaction happens, you form silver on the surface. In this setup, though, we can sneak a device. We can sneak a device in that wire and make use of that electron traveling, the pull of that electron towards the silver, the draw of that electron away from the copper. We can make use of that energy. And again, the reason we do this in volts instead of joules per mole is because, again, physicists started working on this before chemists and thought they were doing something new and unlike anything else, when it was like, no, you're just doing chemistry. But, you know, it's still great. So I like making fun of chemists and physicists and how much they don't get along, because in my undergrad I did chemistry and physics. And so I had classes, like I would take a thermodynamics class in the chemistry department, and I'd take the exact same thermodynamics class in the physics department, and they'd be like, we flipped all of our sign notations, and we decided to use 0 Celsius for our standard. And I was like, they just have these little switches between them, which is just like irritating. So, in any case, we start to label these again with the kind of like experimental setup versus the chemical reactions that are happening. This half, if we split this in half, this is our anode half, and this is our cathode half. Physicists, maybe they realized it, maybe they didn't, but they did not realize that this is where this is where oxidation is taking place, right? The chemical change that's happening. And this is where reduction is happening, right? So that's kind of the chemical knowledge. First of all, chemists did not come up with this. If we just depended on chemists to make batteries, wouldn't have happened, right? If we just depended on physicists to understand how batteries work, wouldn't have happened. It really took chemists and physicists working together to get us to where we are in battery technology today, right? But physicists were the first ones to figure out, like, you could just pile up metals and get electricity out of it. It's pretty wild. It's like the first battery was this thing called a galvanic pile, which is just literally a stack of zinc and copper in an acidic solution. And it works. It's wild. So we get this language. We get the experimental setup, the anode half, the cathode half, the half where oxidation is happening, the half where reduction is happening. But they need to be connected to each other. We never have oxidation by itself and reduction by itself. It's always together. It's always reduction and oxidation together. We know that the oxidation is going to be loss of electrons is oxidation. The gain of electrons is reduction. So we can tell how the electrons are flowing as well. They're leaving the oxidation half. They're going to the reduction half. They're leaving the anode. They're going to the cathode.
Do you have a way of remembering that, like, anode is oxidation and cathode?
Both valves. A and O go together.
Okay.
That's it. That's my trick. C and R go together. They're both consonants. Such a weird word. But in any case, yeah, both valves. That's how I always remember. And then we always try to draw the anode first, and A is the first letter of the alphabet. So.
Is that the same when we do the, like, would it
The
be like,
shorthand notation?
Yeah.
Yeah. So our shorthand notation, let's go ahead and write the shorthand notation for this. So we want to do something that kind of takes this experimental setup, but makes it like quicker to draw, right? It's nice to draw out the whole thing. I can see the wire connecting, I can see the salt bridge, I can see the ions, I can kind of see everything. But once we have some of that knowledge and some of that familiarity, we just go and we say, look, I've got a piece of copper, I got a copper solution, I got a salt bridge, I got a silver solution, I've got silver electrode. That represents the entire setup, right? And again, it's anode and cathode. You can almost see it as the two half reactions, right? I've got my copper to copper 2 plus losing electrons, half reaction. I got my silver plus to silver gaining electrons, reduction, half reaction. You can even kind of draw it like it's I always imagine being able to draw the beakers on it. Right? And then there's my solution. And then I just need my little salt bridge to connect them. Right, so it kind of like, when I see it, it's like you just take a bunch of the setup and you just erase that setup. And it's the same thing. Right, so it really gives this kind of direct relationship to the experimental setup. The full diagram versus the shorthand notation.
So when it gives you like a shorthand notation, but it's not like in order, or like it's like it's not the correct shorthand notation, and it asks to like put it in the correct shorthand notation.
Yeah.
How do you know which one's the anode anode and the cathode.
So there's a couple things we have to watch out for. I think I know which, was this from the problems in class or something else?
I think so. I think there's a few on the MQs and I think on the last.
So it has to, there's two possibilities. Possibility number one is they give you the order where they want it to be anode and cathode. So they give you the anode first and the cathode second and say calculate the standard cell potential for this experimental setup. And for that experimental setup, it could be a positive voltage or a negative voltage. It could be spontaneous or non-spontaneous, right? Depending on how you set it up. Maybe you set it up wrong. Right, if I set this up backwards, so I've got silver as my anode and copper as my cathode, all I'm going to do is end up flipping the voltage. It's going to run backwards. I'm going to end up with a positive voltage, which is going to tell me that it's spontaneous towards reactants instead of towards products. Right? We're just flipping things. But if they do that, they might actually want you to calculate that positive voltage, or sorry, that negative voltage, that non-spontaneous cell potential, kind of talk about your understanding there. Or they say, from these lists of materials, from this thing, make a positive cell potential. Make the most positive cell potential. And the reason we go with positive cell potentials is because we're usually trying to make things that are going to spontaneously work. Because that's where we get that positive cell potential idea coming in. So the problem in class, what I think your mind is on, was saying specifically, put this together to make it so you end up with a positive standard cell potential. So you have to look at it and say which thing is going to get oxidized, which thing is going to be reduced, such that I get a positive cell potential, a spontaneous reaction.
And to do that, you look at the chart, right? And
Exactly.
You see which one has the
right.
higher voltage.
And the higher value is going to be?
The cathode.
Yeah, the higher value is going to be the cathode. It's going to be the reduction half.
Okay.
The
so
lower
I'll
values.
Tell you if it wants it positive. Or
It's got to tell you if it wants it positive or if it wants it as written.
Okay.
Okay.
So then from that you can like figure out if like which one would be the cathode and which would be the anode.
Yeah.
Based on like just the values.
Yeah, and we at this point have pretty much only done positive cell potentials. The place where negative cell potentials get interesting, which I think we're not going to get to until after the exam, is in electroplating, right? Essentially forcing reactions to go backwards. Have you ever gotten like any jewelry that's gold plated?
Mm-hmm.
How do they get the gold on there and have it not be expensive? They do gold plating. They use electrochemistry to put essentially like a couple molecule thick layer of gold on the outside. Molecules might be exaggeration, but they put this really thin layer of gold on it where they essentially dip it into a gold solution, nothing happens. They apply some electricity. The electrons that run across the metal surface pull the gold ions onto it and put a gold plating on it. They shut off the current, and now you've got a thin layer. If you want to make it a thicker layer, you just run it longer, and the gold builds on top of the gold. This is also how you refine minerals out of, or metals out of minerals. So if you go and, I don't know if they say this anymore. Have you ever heard that recycling one can run your cell phone for like 2 days or anything like that?
Mm-hmm.
So the idea is, and we'll look at this again probably after the exam, so not going to be on the exam, but essentially you can look at when aluminum is mined, it's mined as an aluminum ore, so it's like aluminum ions in some it's some mineral that's not aluminum metal. It's like aluminum oxide or an aluminum, I can't remember what it is right now. But you take that stuff, you throw it into water or acidic solutions, you get an aluminum solution, aluminum ion solution, and then you drop some electrodes in there, run an electrical current, and you get aluminum plating on the cathode. And after you run it for a while, you take that out, you scrape the aluminum off that electrode, and now you've got aluminum metal. The amount of electricity it takes to do that is a lot. It's much more electricity than it takes to just take an aluminum can and melt it down and reform it. And so just melting down an aluminum can and reforming it is way less energy intense than trying to pull aluminum out of its ore state. This is why we should all recycle aluminum cans. Plastic recycling, don't get me started, but aluminum cans, that's part of why you can still, even to this day, get paid to recycle your aluminum cans, because it's actually, there are some things that when you try to recycle them, there's no monetary benefit. Aluminum and glass, you can actually make some amount of money off of them, because there's actually a cost benefit to that. And we'll look at that a little bit probably after the exam.
So for this problem, if it didn't give you the balanced reaction and it just said there's AgCu, AgCu2.
There's a silver half and a copper half.
Yeah, and then it asked you to like put the chemical reaction together, and you just flipped it. Like if you had flipped it where it was, you said Cu 2 plus was on the left side and Cu solid was on the right side, you would just get a negative value, voltage value, right? So it's the same thing, just like
Flipped
it.
Right, and we can see that because when we start getting into how we calculate these, right, my E cell standard is going to be my E cat minus my E an. My cathode half minus my anode half. What happens if I flip my cathode to my anode? Negative sign.
Yeah, so there isn't technically one designated cathode or anode, is there? Because either could be the cathode or anode, it would just change the...
Correct. Right, and this gets to the idea of spontaneous reaction, right? Spontaneous versus product favored, reactant favored. So when we write down, and this is again, part of the reason this language gets complicated is in the physics world, spontaneous versus non-spontaneous is usually the preferred nomenclature of like, it's a spontaneous process or a non-spontaneous process. Whereas when we start looking at chemical reactions, we start talking about product favored or reactant favored. So if you set this cell up, and we actually did this when we were doing our wires for our half cell reaction, right? When you set this up and you connect the wires, and it's like, oh, I got a negative voltage, that's not like the reaction is running, like, it's not like the reaction's impossible, that just means it's running backwards from what you think it's doing. That means, so if you set it up, right, no matter which way we set it up, the reaction is going to go that direction. If you set it up backwards, right, so set up this way, it's going towards products. You set it up in the reverse way, it's going to go towards reactants, but the silver solid is going to be what is formed. As long as you have these reactants present. If you set it up backwards but you have no copper ions, nothing happens. Right? So if you like did this, oh actually, yeah, if you set it up backwards with no copper ions, then nothing would happen.
And then when you balance that, or like if you had to balance that, because you were just given like the elements that you're working with, do you have to split it into the half reaction, then balance it, then?
Yeah, that's always the safe way to do it. With these simple metal-metal reactions, I can usually eyeball it without having to do the full half reaction. Okay. But if we got any oxides or hydroxides, definitely I'm going to want to do the half reaction method. Or if I'm even doubting myself, like if I'm doubting myself in my half balancing, I'll also do that. Because this isn't balanced yet, right? I'm going to need a 2 there and a 2 there to balance it.
Right.
Which means if I tried to do any KEQ equations with this, I would have gotten it wrong because my Q value would have been wrong. So how does Q value even come into this? Well, as you can see from this relationship that says KEQ can be related to E cell, we can also do a delta G standard is equal to a negative NF E cell standard. Delta G standard is equal to a negative RT ln KEQ, right? And that's where we come up with this relationship. The free energy of the electron motion, the redox reaction versus the equilibrium constant. And so if you don't have this balanced correctly, you're going to get your KEQ expression wrong. Because I need this to be products over reactants, so I need my KEQ to be copper 2 plus over Ag plus squared. And if I didn't balance, I'd miss that square on bottom and it would totally mess up my calculations. So making sure we've got that plus Ag plus concentration squared. The other thing we can do is we can relate this. I'm going to switch colors because it's getting crowded up here. We can also do, let's do it in green. I haven't used green yet. We can also have delta G equal to RT ln Q over KEQ. And delta G equal to negative NF E cell. Oh, I turned my C into a, there we go. Right, and what you'll notice here is I dropped all the superscript zeros to say that it's standard conditions. So this is a non-standard cell potential. And there's a couple different ways we can get a non-standard cell potential. So I can kind of add a new equation down here, where I can set these things equal to each other. I'm going to flip the board for a second. I'm getting too crowded. And I want to do a step-by-step. I didn't do this in class. The textbook does it, though. Whoa, this is old. The textbook does it, and you're all reading the textbook, right? Yeah, you're all reading the textbook. Doing all the problems in the textbook as well?
No.
Yeah, great. Okay, I'm glad you're all doing it. So we have this situation. We have delta G. Oh, let me just do this. We've got negative NF E cell is equal to negative RT ln Q over KEQ. And what we can do is a little bit of a rearrangement. I'm going to use some natural log rules over here. I'm going to have negative RT ln Q minus RT ln 1 over KEQ. Oh no, I'm okay. I'm okay.
Would it just be?
Isn't it just minus KQ? Yeah.
Right, I can just do a little natural log rule. And here's the crazy part. This can be related back to E cell naught, right? This thing would be equal to standard cell potential. This thing would be equal to NF E cell standard. So I can figure out, I can divide over.
Wait, why does it become plus?
What's that?
Oh wait, actually never mind. I see why it becomes plus.
But that should be plus. I feel like I messed up a negative sign someplace. I feel like I messed up a negative sign someplace.
I don't think so. Because it's minus KEQ. Because you do minus and then this
Yeah,
is negative. So
yeah,
I think
yeah.
that's alright.
Yeah. Well, I still think I messed up a negative sign someplace. RT ln KQ is equal to NF E cell. I'm feeling it. We'll see, because what we're going to end up doing is I'm going to divide by negative NF. So I'm going to end up with, E cell is equal to I definitely dropped the negative
With
sign
the middle, or where it says plus, but not just be minus, because you're adding it, but technically it's a negative.
there. But then I flipped it as well.
Okay.
So then it becomes adding, but I know this equation, so here's where I'm like getting frustrated with myself. I know that this equation is supposed to end up. I know this is how I know I have a negative sign messed up someplace. I know this equation should end up with E cell equals E cell naught minus RT over NF ln Q. And I guess I'm carrying around a bunch of extra negative signs. Ah! That one's not negative. That's why. I found it. Right? Because And this is the, yeah, so that's what it is. So this becomes positive, this becomes negative. That's what it was. Okay. And the reason is, did I erase it already? Let me check. I erased it already. But it's the difference between delta G doesn't have the negative sign, whereas delta G naught has the negative sign. So that was the, I brought over the negative sign I wasn't supposed to. I'm glad I found that. Okay, I feel better. So we end up with this equation. This is the Nernst equation, which is the non-standard cell potential equation. So I can say my non-standard cell potential is going to be related to my standard cell potential minus where my concentrations actually are. Right? My standard cell potential is an equilibrium measurement. Sorry, not an equilibrium measurement. It's a standard conditions measurement. All concentrations equal to 1. So this whole term disappears, goes to 0, because I'm going to have the natural log of 1, which is just 0. And at standard conditions, my cell potential is the standard cell potential. But as I vary away from those conditions of standard conditions, my products or reactants changing their concentration, the concentration of the battery can actually affect my cell potential measurements. Bum, bum, bum. This allows us to do all kinds of wild calculations for what happens to batteries as the temperature changes, what happens to batteries as the concentrations change, what happens to batteries as a chemical reaction proceeds and reactants get used up.
Thank you.
As reactants get used up, my Q value changes. How does that change my voltage? So when we look at standard, we've got our molarities equal to 1 molar. So if I wanted to, so let's go ahead and flip the board and look at this now. Right, so if I was looking at, wow. Like and subscribe. No, I'm kidding. So if we looked at this, I got to give myself a little bit, it's just so professional, you know? I'm going to erase a little bit. I have to get myself a little bit of space here. I'm going to erase that KEQ. I'm going to erase this cell battery here. We can erase all that. We're going to leave that information there for now. If I had my initial 1.00 molarity, 1.00 molarity, that would get me standard cell potential. It's not equilibrium, it's standard cell potential. And then if I did any change in concentration, right? So that's my initial. And then as I change, I'm going to have minus x, minus 2x plus 2x. Right? I can look at my battery as it's changing and say, where does my concentration end up as this proceeds towards equilibrium? Voltage should go to as the battery runs. Do the batteries charge up as they run? No, they charge down. So as this runs, the battery should get lower and lower and lower voltages. So if we wanted to set up a battery that needed to be charged less often, we start with like a lot more silver concentration, a lot less copper concentration, and then the battery would be able to run for a while in this forward direction. But we can track as it changes, as that silver concentration gets used up, as that copper concentration gets created. I'm going to come up with a non-standard cell potential. And again, this becomes a really important spot to make sure we've got our chemical reactions balanced correctly, because our Q value is going to depend on that balanced chemical reaction and the coefficients there.
Okay.
Yeah.
So when you're solving for Q, the coefficients only matter because of the powers, right?
Yes.
And you don't multiply the initial concentration by the coefficient.
Correct.
Okay.
Because we haven't done any, the coefficients only matter when we're taking equilibrium stoichiometry into account.
Okay.
Right? So if I look at the energies of these initial conditions, then it would matter. If I was looking at If I was looking at how it changes, like if I'm just saying how much material do I have, how much you have is how much you have. Doesn't matter. And the analogy I like to use, because I like cooking, is let's say you've got a cookbook that has like a chocolate chip cookie recipe in it. That cookie recipe is the same no matter whose house you go to. But if you go to, if you go to my house, I've got tons of chocolate chips, so you can make a lot of cookies. If you go to somebody else's house, they got no chocolate chips, you can't make chocolate chip cookies. Right? The amount of chocolate chips in your cupboard doesn't care what the recipe is. It's only when you go to make the cookies that it matters how many chocolate chips there are. Does that make sense?
Yeah.
Okay. So yeah. We got a little bit more time. Was that kind of the stuff you were looking for? Was there a specific problem that you wanted to talk about as well, or was that helpful?
I think, yeah, it's pretty good. Like,
Okay.
I had some like concentration problems, but
I just focus
pretty
more.
sure I know how to do this now.
Sorry, that was a bad joke. Yeah, just focus more.
Yeah.
Concentrate.
Yeah.
No, the concentration really comes into the Q value and making sure that we have the Q value set up correctly.
Mm-hmm.
And that is the number one place where I see students make mistakes, is they look at this and they go, okay, cool, I'll do product, since it's a voltaic cell, I'll just do this. And then it doesn't work out right. And they're like, why isn't it working? Why isn't it working? It's like you got to balance and get that squared there.
Yeah.
And then all of a sudden everything starts working. So it's kind of, with the way we went into voltaic cells, it kind of feels like that material is separate from what we've done. But after I have a balanced redox reaction, I'll still write down my KEQ expression is going to be my copper 2 plus at equilibrium divided by my Ag plus squared at equilibrium, right? I'll still write down that expression after I balance the chemical reaction, just so I don't lose track of it as I go through other problems. Doesn't matter for standard cell potential, but as soon as we go to non-standard, really important.
Right.
Okay. Can I ask a question about like the last quiz?
Yeah.
Okay.
I'm gonna go ahead and I know people watching probably want that too, but I'm gonna go ahead and stop recording because office hours are pretty much over and get this posted, and I'll still answer your questions.
Okay.